Today we study Maharashtra State Board Class 10th Science Chapter 1. That is gravitation.
We have seen in the previous standard that the gravitational force is a universal force and it acts not only between two objects on the Earth but also between any two objects in the universe. After much thought, he came to the conclusion that the Earth must be attracting the apple towards itself and this attractive force must be directed towards the center of the Earth. The direction from the apple on the tree to the center of the Earth is the vertical direction at the position of the apple and thus, the apple falls vertically downwards. The force on an apple on the tree is towards the center of the Earth, i.e. along the perpendicular from the position of the apple to the surface of the Earth. The figure also shows the gravitational force between the Earth and the Moon. The distances in the figure are not according to scale. Newton thought that if the force of gravitation acts on apples on the tree at different heights from the surface of the Earth, can it also act on objects at even greater heights, much farther away from the Earth, like for example, the Moon? Can it act on even farther objects like the other planets and the Sun? Introduction to Scientist, Sir Isaac Newton, 1642 to 1727, was one of the greatest scientists of recent times. He was born in England. He gave his laws of motion, equations of motion and theory of gravity in his book Principia. Before this book was written, Kepler had given 3 laws describing planetary. However, the reason why planets move in the way described by Kepler's laws was not known. Newton, with his theory of gravity, mathematically derived Kepler's laws. In addition to this, Newton did groundbreaking work in several areas including light, heat, sound, and mathematics. He invented a new branch of mathematics. This is called calculus and has wide-ranging applications in physics and mathematics. He was the first scientist to construct a reflecting telescope. Circular motion and centripetal force. Tie a stone to one end of a string. Take the other end in your hand and rotate the string so that the stone moves along a circle as shown in figure 1.2a. Are you applying any force on the stone? In which direction is this force acting? How will you stop this force from acting? What will be the effect on the stone? As long as we are holding the string, we are pulling the stone towards us, i.e. towards the center of the circle, and are applying a force towards it. The force stops acting if we release the string. In this case, the stone will fly off along a straight line which is the tangent to the circle at the position of the stone when the string is released, because that is the direction of its velocity at that instant of time, figure 1.2b. You may recall that we have performed a similar activity previously in which a 5 rupee coin kept on a rotating circular disc flies off the disc along the tangent to the disc. Thus, a force acts on any object moving along a circle and it is directed towards the center of the circle. This is called the centripetal force. Centripetal means center-seeking, i.e. the object tries to go towards the center of the circle because of this force. From the above activity, example, and questions it is clear that for the Moon to go around the Earth, there must be a force which is exerted on the Moon and this force must be exerted by the Earth which attracts the Moon towards itself. Similarly, the Sun must be attracting the planet. An introduction to scientists. Johannes Kepler, 1571 to 1630, was a German astronomer and mathematician. He started working as a helper to the famous astronomer Tycho Brahe in Prague in 1600. After the sudden death of Brahe in 1601, Kepler was appointed as the royal mathematician in his place. Kepler used the observations of planetary positions made by Brahe to Kepler's first law: the orbit of a planet is an ellipse with the Sun at one of the foci. Figure 1.4 shows the elliptical orbit of a planet revolving around the Sun.
Kepler's second law: the line joining the planet and the Sun sweeps equal areas in equal intervals of time. A band CD are distances covered by the planet in equal time, that is, after equal intervals of time. The positions of the planet starting from A and C are shown by B and D respectively. The straight lines as and CS sweep equal area in equal interval of time, that is, area ASB and CSD are equal. Kepler's third law: the square of its period of revolution around the Sun is directly proportional to the cube of the mean distance of a planet from the Sun. Thus, if r is the average distance of the planet from the Sun and t is its period of revolution, then T2 R3, that is Sun planet ACF1 F2. Kepler obtained these laws simply from the study of the positions of planets obtained by regular observations. He had no explanation as to why planets obey these laws. We will see below how these laws helped Newton in the formulation of his theory of gravitation. Newton's universal law of gravitation.
All the above considerations, including Kepler's laws, led Newton to formulate his theory of universal gravity. According to this theory, every object in the universe attracts every other object with a definite force. This force is directly proportional to the product of the masses of the two objects and is inversely proportional to the square of the distance between them. Shows two objects with masses m1 and m2 kept at a distance d from each other. Mathematically, the gravitational force of attraction between these two bodies can be written as: force of gravity is equal to g into mass of first object into mass of second object divided by distance square. Here, g is the constant of proportionality and is called the universal gravitational constant. The above law means that if the mass of one object is doubled, the force between the two objects also doubles. Also, if the distance is doubled, the force decreases by a factor of 4. If the two bodies are spherical, the direction of the force is always along the line joining the centers of the two bodies, and the distance between the centers is taken to be d. From equation 2, it can be seen that the value of g is the gravitational force acting between two unit masses kept at a unit distance away from each other. Thus, in SI units, the value of g is equal to the gravitational force between two masses of 1 kg kept 1 m apart. Consider an object moving in a circle with constant speed. We have seen earlier that such a motion is possible only when the object is constantly acted upon by a force directed towards the center of the circle. This force is called the centripetal force. If m is the mass of the object, v is its speed and r is the radius of the circle, then it can be shown that this force is equal to F equals mv2/r. If a planet is revolving around the Sun in a circular orbit in uniform circular motion, then the centripetal force acting on the planet towards the Sun must be F equals mv2/r, where m is the mass of the planet, v is its speed and r is its distance from the Sun. The speed of the planet can be expressed in terms of the period of revolution t as follows. the distance traveled by the planet in one revolution equals perimeter of the orbit 2πr, r equals distance of the planet from the Sun, time taken equals period of revolution equals t. Thus, Newton concluded that the centripetal force, which is the force acting on the planet and is responsible for its circular motion, must be inversely proportional to the square of the distance between the planet and the Sun. Newton identified this force with the force of gravity and hence postulated the inverse square law of gravitation. Free fall is any motion of a body where gravity is the only force acting upon it. In the context of general relativity, where gravitation is reduced to a space-time curvature, a body in free fall has no force acting on it. Gravitational energy or gravitational potential energy is the potential energy a massive object has in relation to another massive object due to gravity. It is the potential energy associated with the gravitational field, which is released when the objects fall towards each other.